Complex numbers have a bit of a mystique around them, don't they? Before learning about them, and even afterward, I think many people view them as this mysterious or advanced number system, mainly useful for solving similarly mysterious or advanced problems. After all, they're built using a strange so-called imaginary number called I, defined as the seemingly nonsensical square root of -1. And though people may fear them, they usually respect them for being these powerful tools that they could never properly understand or wield on their own. But that's just not true. Once you get used to them, complex numbers are actually one of the most elegant and, ironically, simple to use tools in your mathematical arsenal. And personally, I think it's a big shame that more people aren't shown their utility as an ordinary mathematical tool, and instead the focus seems to be on how mysterious and magical they apparently are. So in this video, I'd like to share the less mysterious or magical side of complex numbers, and show how I've often found them handy to solve some tricky, but still very ordinary, problems. To show that their use is not limited to just quantum mechanics, advanced differential equations, or something like that. That they can be very friendly tools that everyone should feel comfortable having in their mathematical toolkit, and how not knowing them can be a real handicap sometimes. Note that for this video, I will be assuming you know a little bit of basic calculus, mainly derivatives, but even if you don't, I'll be trying to present things from an angle that you can hopefully still follow and get a lot out of. Alright then, let's get started. To start things off, let's review the basics of what complex numbers are and how they operate on each other. The basic building block of complex numbers is I, the square root of -1, an imaginary number, if you will, that has the special property that multiplying it by itself yields -1. It can be added to itself and multiplied by real numbers to get other imaginary numbers that are multiples of I, like 2i, 3i, -4i, or 6.28i. You get a so-called complex number by adding a real number and an imaginary number together, like 3 plus 4i or -1 plus 1.5i. These expressions are treated as atoms. They don't simplify any further, and you can visualize them as points in the complex plane, where the x-axis tracks the real part, and the y-axis tracks the imaginary part. From this perspective, we can define the absolute value of a complex number as how far away it is from 0, or the origin, within this grid system, which you can compute by using the Pythagorean theorem on both the real and imaginary parts. So for example, the absolute value of 3 plus 4i works out to be 5. Now, two complex numbers can be added together by adding their corresponding real and imaginary parts, similar to how adding two vectors works. But unlike vectors, you can also multiply complex numbers together to get another complex number. And it works how you might expect by following the distributive rule and remembering that I squared is actually -1 and simplifying from there. It might not be clear yet what complex number multiplication means geometrically, just looking at these 3 points, but it actually has a very straightforward interpretation, which will be key to their geometric usefulness. To understand it, take a complex number z, like 3 plus 4i here, and multiply it by a complex number w that sits on the unit circle. That is, a complex number whose absolute value is 1. You might notice that the product zw looks like a rotated version of z. And indeed it is. In fact, multiplying z by w rotates it around the origin by the angle w makes with the positive real axis. In this case, an angle of 70 degrees. So multiplying a complex number by a complex number of absolute value 1 just rotates it. This makes complex numbers a useful tool for representing and computing two-dimensional rotations. For example, if you want to calculate the coordinates of where a point like 2, 3 ends up after being rotated, say 30 degrees counterclockwise around the origin, all you need to do is find the complex number on the unit circle that is 30 degrees counterclockwise off the positive real axis and multiply it by 2 plus 3i. If you know a little trigonometry, this isn't too hard to do. The xy coordinates of the point 30 degrees along the unit circle are given by the cosine and sine, respectively, of 30 degrees, which work out to be about 0.87 and 0.5. So our point W can be expressed as the complex number 0.87 plus 0.5i. Multiplying it by our original point 2, 3, expressed as the complex number 2 plus 3i, we get that it's about 0.2 plus 3.6i. And looking at the picture, it matches up with where 2, 3 ends up after being rotated 30 degrees. Now, since this is such a common thing to do with complex numbers, it would be handy to have a shorthand way to refer to the complex number on the unit circle that is a given angle theta away from the real axis. And luckily, we have one. If you raise e to the power of the imaginary number theta I, where theta is measured in radians, the complex number you get is cosine of theta plus I sine of theta, which are the precise coordinates of the point we want. This relationship is called Euler's formula. Now, I won't go into why Euler's formula is true in this video. Anyway, there are already many other resources that can explain it probably better than me. But for now, you can think of e to the theta I as a funky way to represent the complex number on the unit circle that is theta radians counterclockwise from the positive real axis. But as you'll see later, there's actually a very good reason for thinking of it this way, besides just shorthand. Now, as for multiplying by complex numbers that are not on the unit circle, it's the same basic idea. You rotate by the angle it makes with the positive real axis, but then you also scale the rotated point away from the origin by the absolute value of the number that multiplied it. For example, multiplying the complex number 3 plus I by -1 plus 2i produces -5 plus 5i, which is what you get by rotating 3 plus I by the angle -1 plus 2i makes with the positive real axis, and then scaling it up by the absolute value of -1 plus 2i, which is square root of 5 in this case. This is the key geometric interpretation of complex number multiplication. Multiplying by a complex number rotates and scales a point, as opposed to real number multiplication, which only scales. So complex multiplication provides a very natural way to describe two-dimensional rotations. And because of this, complex numbers are often super useful for problems involving rotational motion or rotational symmetry. Complex numbers are the language of 2D rotation. To see what I mean, consider this example. Let's say you have a point moving in 2D space around the origin in some kind of irregular way. Maybe it represents the motion of a charged particle in an electric field or something. Let's say the point's xy position at any time t is given by two functions, x of t and y of t, and we want to compute its angular velocity around the origin at any time t. That is, how fast the angle it makes with the positive x-axis is changing at any given moment, or the time derivative of the point's angle function. To compute this, we would presumably need to first calculate the point's angle function at any time t from its two xy position functions, so we can then take its derivative. There's some subtlety required to do this right, which I'll skip over, but it can be done. It's possible to define a function that takes the xy coordinates of a point and outputs an angle in the range 0 to 360 degrees, or 2 pi radians, representing the counterclockwise angle the point makes with the positive x-axis. Throw in x of t and y of t into this function, and we have our angle function, theta of t. But here we run into a subtle problem. This angle function is not continuous. If x is positive and y moves from being negative to being positive, the computed angle will abruptly switch from being around 360 degrees to being around 0 degrees. So if you're trying to measure the angular velocity by, say, measuring how much the angle changes in a short period of time, but the point happens to be very close to the positive x-axis, you can wind up comparing angles from two sides of the seam and accidentally calculate a wildly wrong angle difference. What we'd really like is for the angle function to not wrap around to 0 if we started from around 360 degrees. But unfortunately, there's no way to easily do this. Angles are cyclic by their very nature. 405 degrees is the same as 45 degrees, and there's no real way to tell the difference between them without remembering the entire prior history of the point's motion, which would be a hassle. So are we stuck then? Is there no easy way to calculate a local change in angle just using local information about the point's motion? Well, turns out there is a way. The trick is to calculate the derivative of the angle function indirectly without having to know its full angle function in advance. And complex numbers provide a sneaky way to do just that. To do it, first package our two coordinate functions, x of t and y of t, into a single complex valued function, f of t, which outputs x of t plus I y of t for any given t value. Now, observe that we can always express a complex valued function in polar form as r of t times e to the I theta of t, where r of t is just the absolute value of f of t, which is just square root of x of t squared plus y of t squared in this case, and theta of t is the full angle function of the point, which, remember, we're trying to avoid computing directly. If you take a step back, this formula should make sense, right? E to the I theta of t is a complex number on the unit circle that makes the same angle with the positive x-axis as our point. And if we scale it up by r of t, the point's distance from the origin, it will coincide perfectly with our point. Okay, now here comes the trick. Take this polar equation for f of t and divide both sides by r of t to get f of t over r of t equal to e to the I theta of t. Now we'll take the derivative of both sides. One of the really nice things about complex numbers is that many of the algebra and calculus rules you're used to for real numbers and functions work in exactly the same way in the complex setting, and derivatives are no exception. Even though all the functions here are complex valued, the familiar derivative quotient rule applies. So on the left-hand side, we get the usual expression f prime r minus f r prime divided by r squared. But what's really cool is the exponential derivative rule works the same old way as well. On the right-hand side, the derivative of e to the I theta of t will just be itself times the derivative of I theta of t in accordance with the chain rule. And since I is a constant, it just becomes I times the derivative of theta. Do you see now why writing a unit complex number as e to the I theta is so useful? Now, remember our goal is to compute theta prime of t, the derivative of theta, without having to know what theta of t is in advance. And at this point, we can actually get rid of the explicit theta of t that remains in the equation. Before we took a derivative, remember how we had f of t over r of t equal to e to the I theta of t? Well, it means we can substitute f over r for e to the I theta right here in our new equation, giving us f of t over r of t times I theta prime of t, equal to the quotient mess on the left-hand side. From here, with a little rearranging, you can solve for I theta prime of t and get that it equals f prime over f minus r prime over r. But now we can make an interesting observation. Although f and f prime are complex valued functions, the functions r of t and theta prime of t are purely real valued. By themselves, r and theta prime just represent radius and angular velocity of our moving point. Perfectly real, nothing complex about them. And since our real valued theta prime of t is being multiplied by I on the left-hand side, the whole expression must be purely imaginary. So theta prime itself can be extracted by taking the imaginary part of both sides. And since r and r prime are both purely real valued functions, subtracting r prime over r will have no effect on the imaginary part of f prime over f, so we can just drop it. And in the end, we get a really nice compact little formula that will compute the derivative of theta directly from f prime and f without having to touch the original full theta function at all. And remember, f of t is really just x of t plus I y of t. So really, we found a way to compute the angular velocity directly from the x and y coordinate functions. Isn't that neat? But does this formula really make sense though? I mean, if we take a step back, why should this wacky expression have anything to do with angular velocity? And if you don't know calculus, this may all seem like black magic anyway. So let's see if we can figure out what each piece of this formula is doing and why. F of t and f prime of t represent the position and velocity of the point at any time t. So let's label them in the picture with two vector arrows, blue for position, green for velocity. Now, in our formula for angular velocity, we divide f prime of t, the velocity vector, by f of t, the position vector. Ignoring scaling, remember that multiplying by a complex number results in a rotation by the angle it makes with the positive x-axis. So dividing by a complex number does the opposite, a rotation by the same angle but in the opposite direction. So dividing f prime by f rotates the velocity vector backward by the position vector's angle. Now, since the position vector is presumably not a unit vector, dividing by it will also scale the velocity vector down by the magnitude of the position vector. But let's ignore that for the moment. Continuing with our formula, we then take the imaginary part, which grabs the vertical component of this rotated velocity vector. But since the velocity vector was rotated backward by the angle of the position vector, the vertical component here really represents the component of the original velocity vector in the direction perpendicular to the position vector. And since the position vector always extends radially away from the origin, the velocity component perpendicular to it really represents the circular component of the velocity vector around the origin at time t. But now remember that, in reality, dividing by the position vector also scales the velocity down by the magnitude of the position. That is, by the current radius of the point away from the origin. And dividing the circular speed of an object by its radius of rotation yields its angular speed, just like how dividing the length of a circular arc by its radius yields the arc's angle in radians. So this little formula is really a compact and elegant way to extract the circular component of velocity and then divide it by the radius to obtain an angular velocity. Isn't that clever? But what I love is how you don't even have to be that clever to come up with this formula. If you know calculus and aren't afraid to use complex numbers, this sneaky little formula just pops out like magic from taking the derivative of the polar representation of the position function. If that's not a testament to the power of complex numbers, what is? So I hope that gave you a taste for how complex numbers can succinctly describe geometric relationships and provide a really natural and elegant language to describe 2D rotational dynamics. But I could go on with so many other examples. Like how dividing two complex numbers encodes the rotational action between them, providing a clean way to rotate a point by the angle between two vectors. Or how they provide a unified way to represent both rectangular and polar parametric functions, something we already saw a little in this video. Or how they make describing epicycles really easy, which is essentially what Fourier series are built from. Truly complex numbers are just such an ideal language to describe so many two-dimensional scenarios, and I find them an indispensable tool for this reason. As a matter of fact, Morpho, the software library I wrote to create most of the animations in these videos, encodes almost all 2D positional data as complex numbers just because it's so easy to manipulate in that form. But as great as complex numbers are, I should mention a limitation they have. Although they describe 2D rotation extremely well, they're really pretty much limited to just 2D. By themselves, they can't faithfully describe 3D rotations. The tool for that is the quaternions, the big brother of complex numbers, which we don't have time to discuss in this video. Still, I hope you came away with a better understanding of just how wide the utility of complex numbers is, and how much you could be missing out on without a working understanding of them. Really, they don't have to be all that complex, and once you get used to them, they start to feel like old friends. Hey everyone! So I have a bit of an announcement to make. Morphocular now has a Patreon page. Over the past several months, it's pretty fair to say I've been blown away by the impact and reception these videos have gotten, as evidenced by the recent rapid growth of this channel. It's been quite the ride for me, who hadn't dared hope to make such a large impact in so short a time. In light of the value these videos clearly seem to have for so many people, I'm very eager to continue making more and better ones going forward, as creating them is a genuine joy for me. Though, as you can imagine, creating them also takes a big commitment of time and energy, at least if they're going to be at the level of quality I'd be satisfied with. And as this channel is currently run by only one person, it can sometimes be hard to justify spending the time to make these videos between other priorities of life. So if you find value in these videos and would like to be a part of enabling me to create more of them, consider becoming a patron with a monthly contribution of whatever you're comfortable with. As a small way of saying thanks, you'll get to see and provide feedback on new video drafts before they go public, view some behind-the-scenes content such as work-in-progress animations or cut material, and be first in line for any experiments I might want to try out with the channel in the future. But at the same time, don't feel pressured to join up on Patreon either. Simply watching and sharing videos and subscribing also makes a meaningful difference. But if you feel you'd like to go a step further, I'd be honored to have you join as a patron. In any case, thank you all, truly, for watching and being a part of this little experiment of a YouTube channel so far. Take care, and I'll see you all in the next video.